So I'm going to present our work, uh, the Throughput-Optimal broadcast in dynamic wireless networks. Okay. The first, I'll be focusing on the restricted case called directed acyclic graph. In my next talk, I'll focus on the general problem with general topology. Okay, so here is a brief outline of my talk. First, I'll introduce a problem, like what is a broadcast problem is and what it is all about, why is it is important. And then I'll talk about some preliminary work and some preliminary results concerning this problem. Then I'll detail some prior works on this problem. This is a classical problem, lots of work, prior works. Then I'll describe a throughput optimal algorithm that we actually designed for dynamic network, dynamic wireless networks. And then I'll detail some capacity characterization of wireless broadcast capacity that just falls as a just a consequence of our algorithm. And then I'll show some numerical simulation. Finally, I'll conclude my talk with some pointer to some future work. Okay, so let's get started. So what is the problem all about? So the problem is basically efficiently disseminate packet that are arriving as a source to all nodes in a network, in a multi-hop network. Okay, so why is it important? It is basically a fundamental problem, and it has applications in wireline networks, say in live multimedia streaming, software updates, in-network function computation. Right now, this problem is getting a lot of importance. And now you can see a cartoon here. So here is the source, and here are some set of nodes. Say is the internet router, and you'd like to send this message to everyone. Okay, in a multi-hop fashion. The problem becomes even more interesting in the wireless case because unlike the wired counterpart, the links and the network topology is not fixed. So these links are basically changing with time according to say some process, some random stochastic process. And we are particularly interested in these challenging scenarios, how to do optimal broadcast in this dynamic wireless network in an interesting fashion. So in wireless networks, we have applications, especially in military domains, for example, in military communication, disaster management in mobile ad hoc networks, etc. Okay, so now I'll get started with the wireless network model, the very simple model and standard model that you actually consider. So the network topology is represented by a directed graph. V is as usual the set of all vertices and nodes, and E is a set of edges. I'll talk about the edges much more in detail. So time is slotted. We consider it basically a discrete time system. Time is slotted, and packets arrive randomly at a source node R, distinguished source node R, according to some stochastic process, accounting process of rate lambda. Okay. The nodes can, so these are the capability of the nodes. The node can duplicate and relay packets to their neighbors. Now the packet transmission. So we consider point-to-point links. For example, think of 60 gigahertz networks where we have directed antenna. So we have point-to-point links, and these links are subject to wireless interference constraints. What do you mean by that? Suppose consider I have this network. Okay. Now I cannot activate all the links simultaneously in a wireless network because of interference, mutual interference. So only a specific subset of links can be activated together at a slot. So what are, for example, suppose I have a primary interference constraint, that is a matching constraint. So under the primary interference constraint, I have three possible maximal matchings that can be activated together, and they are this. So the first one is I can activate these two links together. So we can only, in primary interference constraint, we can only activate the links that are not sharing any nodes. Okay, so you can activate RA and BC. You can see they are not sharing any nodes. Similarly, we can activate RB and SC, or similarly, we can activate RC and AB. Okay, so these are the possible activations under the primary interference constraint that is possible. The algorithm that we will be developing is general, so it works not only for primary interference constraint but for any general interference constraint. Okay, so now I'll be introducing the time variation into our model. So the channel states vary with time in wireless network, as you all know, because of random fading, shadowing, and node mobility. And to model this, we considered a very simple framework where the link could be on or off. Okay, so the set of all possible network configuration will be denoted by the set xi, and the network configuration process is assumed to be a stationary and ergodic process. Okay, that has some unknown probability distribution, possibly highly correlated p sigma. Okay. So let's give you an example. Suppose I have a very simple wireless network. So I have two links. So at most there could be four possible network states. What are they? I mean, they're on or off, right? So we can have like this link is on, only this link is on, or both the links are on, or none of the links are on. Okay, so these are the possible, these are my xi. My xi consists of these four possible configurations and these sigmas vary with time according to some stochastic process. Okay, so now the preliminary, some preliminary work. So what is the broadcast capacity that you are actually targeting? So we know that since it's a broadcast, I have to send the packet to everyone. Lambda star, if the broadcast rate is lambda star, it cannot be more than max flow from R to T. R is a source and T is any node in the network. And this inequality should be valid for all nodes in the network, so I can take the mean to get a tighter bound. And there is a theorem, a very famous theorem from 1965 called Edmonds-Strebecking theorem. It says that this inequality is actually satisfied with equality. So the broadcast capacity is really given by the right hand side. And there exists lambda star number of edge region spanning trees to achieve this broadcast capacity. Okay. Again, an example, suppose I have this network. If you just compute the mean of max flow, it comes out to be 2. So where max flow, this is my source and all others are destinations. And according to Edmonds-Strebecking theorem, it guarantees 2 edge region spanning trees. So these are 2 such edge region spanning trees, and you can actually send packets along these trees to achieve the broadcast capacity. Okay, this is for the wired network, very trivial setting. Okay, so what are some prior works have been done on this setting in wired and wireless? So there is a work by Shashwati Sarkar and Leandro Stossilas in Transaction Information Theory in 2002 that actually pre-computes the set of some spanning trees offline in wireline networks, and they have a back pressure type of algorithm that actually routes packet over the set of all the trees, the spanning trees that they are maintaining. Okay, so for example, suppose these are the trees, these are actually input to the algorithm, and they have an optimal algorithm that can distribute the packets over these 3 trees only. Okay, so why is it not good? Because to achieve the capacity, potentially I have to list exponentially many spanning trees, and so therefore it is definitely large and time varying. When the network is time varying, it is definitely not feasible to do that. And the wireless case is studied with a fixed activation schedule only. So there is a paper by Don Tousley and Andrew Twig in 2008 that gives you an activation schedule that is fixed a priori. Okay, and there is an algorithm that actually on top of the activation schedule, it does optimal forwarding of packets. So what do? We design the first online local control algorithm to achieve the broadcast capacity in time varying wireless DAC for this paper. Okay, so what is the algorithm? Okay, so before I do describe my algorithm, let's consider the feasible policy space. What my policy is supposed to do. My policy can do 2 things at a given slot. These 2 things repeatedly. The first is a link activation. Okay, so it activates a subset of feasible links. For example, a matching subject to the underlying interference constraint. And once you have actually activated a set of feasible links, you schedule packets over the activated links. Okay, so now I'll be considering this packet scheduling component in detail. So I say a general packet scheduler is very hard to even describe, not even derive. So let's see why is it so. So suppose I have a general, there is no constraint I am putting on packet scheduling. Then the state space, so the packet scheduler is a mapping, the set of all possible packets in the networks to the next actions that you forwarding action that you choose. So it's a mapping. So its domain is basically the set of all possible packets in the distribution in the network. So it is exponential in the number of, at least in the number of nodes. Okay. So in this context, suppose this is at a given time slot, this is my configuration of packets in a network. So it's arbitrary. Okay. Suppose my link activation component says me activate these 2 links, RC and AB. Now the packet scheduler has to pick one packet. So either from 3, 4, 5 to send here, or 1 or 4 to send there. As you can see, as the number of packets in the network increase, even to describe this packet scheduler, it is hard. This mapping is hard to describe without any structure. So the thing that we need to do, we have to put some structure. What is the best structure or the simplest structure we can actually put? So here we consider the policy as pi in order. Okay, the pi in order is very simple. When a packet comes that is injected in the network, I give it a number, the index, okay? And I put the constraint that a node can only receive packet number P if and only if it has received packet number P minus 1, okay? So this is very simple. So I can only receive packets sequentially, okay? So this is my very simple policy space. And again, like the example, suppose under the policy space, it will always be the case that the set of received packet by a node is of the form 1 to k, where k is some natural number. So you can see it is 1 to 5 at the source, 1 to 2 at node B, only packet have 1 have been received at packets node C, and 1 to 3 in node A. Okay, and if I am operating with my pi-in-order, any policy in pi-in-order policy space, then my packet scheduling becomes really trivial because my packet schedule, because I can only receive the next packet that I am missing. So node 1 can only receive packet number 2, although 3, 4, 5 are present. node B can only receive packet number 3, although there is only one packet present, right? So it can actually receive that. Okay, so my packet scheduling becomes trivial, and the network state that was initially the set of exponentially many, the set of all packets present in all subsets of the nodes, right now it can be completely described by this vector. ST is R1T, R2T, where RIT is basically the latest packet received at node I up to time t. So this is just a vector of numbers, and this completely describes your network state. There is no, you don't have to describe the network state by listing all the possible packets present in all subsets of nodes. Very interesting. So it is very easy to describe, but the real question is, does there exist an optimal policy in this pi inner policy space? Okay, so that's what we first prove. We prove that yes, there does exist a pi inner optimal policy that resides in pi inner policy space if we restrict our topology to be a directed acyclic graph. Okay, and to prove this, we actually considered another subspace pi star that is defined as follows. Okay, I'll not tell what it is. I'll just give you the example that will be clear. So pi star means a node D can only receive a packet if and only if this packet has been present at all of its in neighbor. Okay, so you look at node D. So it has 3 n numbers A, B, C. A has received packet 1, 2. B has received packet 1, 2. C has received only packet 1. Okay, so that means packet 1 is present all of its in neighbor, but packet 2 is present at node A and B, but not at C. That means node D, according to pi star policy space, node D can receive packet number 1, but it cannot receive packet 2 yet. Okay, this is my restriction I am putting. Why? It will be clear because, so just to summarize, so here is a set of all policies. Here is a set of all policies, pi. Now I have a smaller policy space sitting inside pi, this is called pi in order. Then I have another smaller policies, the policy space sitting inside pi star, pi in order called pi star, and I show that there exists an optimal policy in pi star if your underlying topology is a DAG. Okay. So how do I do this? So I need to define some state variables. Some state variables I define as follows. So RIT is a number of packets, as I have described earlier, number of packets received by node I up to time t. So we define the state variables, n state variables, mean of RIT minus RJT, and IT star j is simply the node that actually achieves the minima. Then the first theorem we prove that although there is no queuing. So the interesting thing in broadcast is that traditional queuing theory doesn't apply because of work conservation doesn't apply. Once a single packet goes in, multiple packet comes out. But the interesting thing is that if we restrict ourselves to pi star in a DAG, then these state variables, xjt, they actually satisfy the linear recursion, that is a queuing recursion. Okay, and in our second lemma, we show that if you can stabilize these state variables, so this xt not only linear recursion, this follows, this actually evolves like a Markov chain. And if you can, if there exists a policy of transmitting the packets, activating the links in such a way that xt, these state variables are stabilized, that is positive recurrent, then that means it is a throughput-optimal broadcast algorithm in a directed acyclic graph. Okay, so that means the state vector xt mathematically corresponds to queue sizes in traditional queuing network. Although I again emphasize there is no queuing per se as we are aware in the data networks. Okay, because packets are basically multiplying. Okay, so now our next task is how to stabilize, how to get a stabilizing algorithm for stabilizing the state vector xt. This is actually done using Lyapunov drift technique. So you define a Lyapunov function, sum of quadratic Lyapunov function xj squared of t, and if I take the drift and I do some calculations, so this is the policy that is actually stabilizes for all arrival rate lambda less than lambda star. So I actually put an weight that is given some state, some function of the state. I'm not going to describe like what is the intuition behind it. It just comes out, but it can be given some intuitive explanation. Then I choose a max weight activation with the weights given by these numbers. Okay. Next, it is our fundamental theorem that we show that the policy pi star is a optimal broadcast policy for DAGs. That is, it achieves for any lambda less than lambda star, the rate of packet reception at node I for all node I is equals to lambda, that is input rate. Okay. Also, as a direct consequence of our algorithm, we have some really nice capacity characterization of broadcast capacity of wireless DAGs. So the first thing is that suppose I have a wireless network and it is a DAG, then the broadcast capacity is actually dictated by the minimum in degree of the node. So minimum in degree is always upper bound on the cut, upper bound on the capacity, right? So we have many cuts, and if your in degree of a network is say 10, your broadcast capacity cannot be more than 10. Why? Because that's the maximum number of amount of packet that a node can get. And we actually show that this is tight. So if I take the minimum of in degree in a wireless network, so this is basically saying the same thing, but in a wireless context. And not only that, as a consequence of this theorem, we have lambda star DAG that it can be computed in polytime under primary interference constraint when we have polynomial linear network configuration. So we have a polytime algorithm for computing the broadcast capacity in a wireless DAG, in a time varying wireless DAG. And the proof uses an LP formulation of this equation, and polytime separating oracle, that is a well-known separating oracle that is also due to Edmonds for the matching polytope. Okay. So now some approximation to broadcast capacity. Why do we need approximations? Because our previous theorem only holds when the number of network configuration is polynomially bounded. So it might not be always the case. For example, suppose I consider the situation where all the links are on or off. Then there are exponentially many network states. That is, xi is exponentially large. In that case, our previous computation doesn't hold, but we can obtain a bound. So for example, consider the situation that the links are arbitrarily correlated, but the marginal probability of a link being on is equals to p. Then we can say that we prove that your broadcast capacity of a network is actually upper bounded by lambda star stat. Okay, lambda star stationary, and lambda star stationary is basically the same, the broadcast capacity of the network for the stationary scenario when all the links are on with probability p equal to 1, and it is lower bounded by p times of that. Okay, so this directly translates to a p approximation algorithm for computing the broadcast capacity. Okay, now I'll show some numerical simulation. So consider this situation. I have some wireless network, and I arbitrarily find 5 trees in the network. And I actually apply the Tossilus algorithm on this network, and I see how the delay property actually, what is the best. So our algorithm is throughput-optimal, and it can be shown that in this particular network, these 5 trees are also throughput-optimal. So how they compare on the basis of delay. So this is our delay performance. As you can see that when I use even 5 trees, the delay is definitely much better than their algorithm. And now this is a situation when I have a wireless network with time varying connectivity, and this is, we can show that the capacity of this network is given by 0.4. So our algorithm, actually this blue curve, it achieves the full capacity of the network, and these 2 lines are for time varying case with different probability of on values. Okay, so now I conclude my talk by saying that classical algorithms require offline computation of spanning trees, which is practically infeasible for the large dynamic networks. What we have derived is a first online probably optimal broadcast algorithm that is for DAGs, the dynamic topology. And we have characterized it both mathematically and algorithmically, and the immediate next step would be to extend DAG algorithm to networks with arbitrary topology. That I'll be going to describe in my next talk.